Now we'll talk about some of the basic concepts of ASME Y14.5 standard. Let's see first the concept of feature. It is any physical portion of a part, as an extrusion, face, hole, slot, etc. Here are some examples of both flat and curved surfaces. FOS, feature of size, a surface of a cylinder or sphere, two opposite parallel elements or two opposite parallel surfaces. It can be either internal or external. Which brings us to the features with no size or simply features. Some examples are fillets, complex surfaces, etc. With this, we have defined features and features of size. Features of size can be internal, as in the case of the holes, or external, such as pins or extrusions. And they always have a size, so they will have size tolerance. Next, we'll see some ways to specify this. First, we have the symmetric tolerance, which has the same tolerance, both positive and negative. Second is the bilateral or asymmetrical, which has more tolerance in one of the two directions. Limit tolerance is where both upper and lower limits are specified. The maximum specifies only the upper limit of the dimension, in which if it's the case and the measured feature were 0, it would be acceptable. The minimum specifies only the lower limit, in which the feature can measure any higher than this limit value, even if it's 500 or 5000. And finally, fit tolerances are shown, in which consideration is left to the manufacturer about the maximum and minimum size according to the setting assembly. Commonly, this kind of tolerance is used to drill holes for dowel pins. We have three common specifications: LF or loose fit, SF or slip fit, PF or press fit. In the first case, the pinhole assembly is loose. The pin can slide freely. In the second case, the assembly is tighter. The pin slides with some work. And in the third case, there is interference between parts. The pin is bigger than the hole, which requires the use of a press to make them assemble. Now, we'll see a couple of dimensions that have no tolerance. Dimensions enclosed within parentheses are known as reference dimensions. They are for informational purposes only, and it means that the official dimensions are located in another view or in another feature. They should not be considered as official dimensions, and its use should be minimal to avoid confusion. The second case of dimensions without tolerance is the basic dimension, which is a theoretically perfect dimension. They're used when we apply a geometric tolerance on a feature. And they can also be identified from a note, such as, unless otherwise specified, dimensions without tolerance are basic. Outside of these two exceptions, all the dimensions shall have some tolerance indicated. As you can see, the holes, which are internal features of size, have a geometric tolerance that controls the location. Therefore, the dimensions that are locating these features shall be basic, since the tolerance for this feature is specified in the geometric tolerance. On the other hand, we can see the dimension which defines the size of the holes is not basic, and it has a symmetrical tolerance of ± 5,000. Keep in mind that geometric tolerance does not necessarily define the size of the feature. FOS and material conditions. We talked about the features and features of size, external and internal. In the previous case, the holes are internal features of size, with upper limit of 0.265 and the lower limit of 0.255. Now, we'll talk about material conditions that can be applied to the features of size. As with all features of size, we can only have two limits, upper and lower. We have two possible material conditions. Maximum material condition, or MMC, is when the feature has the maximum amount of material, and least material condition, or LMC, when the feature has a minimum amount of material. The material condition is related of whether the feature of size is internal or external. A tab has more material and its size increases, but a hole contains more material as it is smaller. Now, let's answer the following exercise, determining the material conditions of some of the features of size step by step. Use the printed exercises as support. First, identify on each of the 5 dimensions shown the upper and lower limits. As an example, in dimension A of 0.55 minus 0 plus 0.05 gives us a limit of 0.55 and 0.60. Now pause the video to perform this part and resume when finished. Check your entries. In the case of feature B, the limits are 0.53 and 0.43. In feature C, we have 1.05 and 0.95. In feature D, 0.29 and 0.19. And in E, 0.34 and 0.24. Second step. Identify each feature of size, whether it's internal or external. As an example, feature A is external. Pause the video now and resume when finished. Check your results. Feature B is internal, C is external, D is external. It can be appreciated in the isometric view. And case E is internal because it is a hole. Third and last step. Place next to each limit if the dimension corresponds to the maximum material condition or least material condition. Please check first if the feature of size is internal or external. Let's use feature A again as an example. Since it's an external feature, the MMC is in the limit of 0.60. And because this is where this feature contains more material, therefore their LMC is 0.55. Now pause the video and resume when finished. Check out your results. Feature B is internal, so as it gets smaller, more material exists in the part. That's why the MMC is 0.43 and the LMC is 0.53. Feature C is external. As it gets larger, more material it has. Therefore, its MMC is 1.05. D is external feature. So, LMC is 0.19. And finally, feature E is internal. Its MMC is 0.24 and LMC is 0.34. This concept of MMC and LMC will be widely used when we talk about geometric tolerances and the use of modifiers. Feature Control Frame, or FCF. It's where the information about the geometric tolerance is shown, starting with the geometric tolerance in the first box. Next, the shape of the tolerance zone. If a diameter is specified, it means that the area is cylindrical, otherwise it is planar. Next, we have the size of the tolerance zone, which is a numerical value. After this, the material modifier. It's the condition of material to which the value of the geometric tolerance applies. And at the end, we have the datums, in the order in which they should be restricted on the part: primary, secondary, and tertiary. It may be 1, 2, or up to 3 datums. Now, we'll see the symbols of the 14 geometric controls. They can be classified into 5 categories: form, profile, orientation, location, and runout. So first, we have the form tolerances: straightness, flatness, circularity, and cylindricity. Profile, either of a line or a surface. Orientation, we have angularity, perpendicularity, parallelism. We also have tolerances of location, position tolerance, concentricity, symmetry. And finally, we have the circular, runout, and total runout. Next, copy the table shown in the appropriate format with the name and its symbol. Here we have some examples of geometric tolerances. Flatness tolerance of 5 thousandths, straightness of 0.02, cylindricity of 0.2, perpendicularity with a diameter of 5 thousandths relative to datum A, position tolerance with a diameter of 5 thousandths relative to datums A, B, and C, total runout of 5 thousandths relative to datum A, profile of a surface of 0.5 relative to datums A, B, and C.